Let's do one more for today. Let's go back to integrating on the x-axis. Nice and familiar, but let's complicate things in a different manner. This region is enclosed by the curves y equals x and y equals x squared. So right now this is just describing something in the two-dimensional plane. And we're going to rotate this shape around the x-axis. We want to find the volume of this solid. So, well, first of all, what does that even look like? I can picture y equals x. I can picture y equals x squared. And here it is graphed for me. The problem didn't say what my bounds were. So I'm going to use the two intersection points for the two different curves. Y equals x and y equals x squared, those two different curves, they both meet at the coordinates 0, 0 and 1, 1. So here in my picture, I have my curves, I have my intersection. We've filled in the region here in blue, and then there's sort of a three-dimensional picture. It kind of looks like a horn on the end of a trumpet or something. I'm feeling kind of musical today. Now, my method says slice it up, see if you can slice along the x-axis, and figure out the area of those cross sections. So this time when I slice, notice that there's a hollow spot inside this shape. It's what I get from rotating that parabola around the x-axis. So this time around, my area looks like, well, it's kind of like a donut. It's flat, right? I've got one circle nested inside of another circle with two different radii. How am I going to calculate the area of this? I only want the area that's shaded in pink here. Well, I can calculate the area enclosed by the larger circle, and then I'm just going to subtract off the area enclosed by the smaller circle. Easy peasy. What are those radii? Well, one of those circles has radius equal to x for my y equals x function. That's going to be my larger radius. The other of them has radius equal to x squared, and that's going to be my smaller radius. X squared is less than x for numbers between 0 and 1. And I can see that in the picture. Okay, so my area function must be pi times x squared minus pi times x squared squared. But I can factor out a pi and say this is pi times x squared minus x to the fourth. This is my area function, and just like before, I'm going to integrate it between my two different bounds with respect to x, and that will be the volume of this region. So my volume is pi times, well, my antiderivative is x to the third on 3 minus x to the fifth on 5. I'm evaluating at 1 and 0. Altogether, I get twice pi on 15.